This video is about how we can write a series of complex numbers in different forms. We're going to do 3 examples, but before we get to those, we need to do a little bit of backstory. We need to remind ourselves firstly about the sum of geometric series. So just a quick reminder that a general finite geometric series looks like this, and the sum is given there. It can be written in 2 different forms. If you need a recap on this from our regular A-level maths, I will post a link to the video in the description to this. If we have an infinite series, then the sum is given by the formula a over 1 minus r. You can only find the sum of an infinite series if it is convergent when the common ratio is less than 1. Also, a couple of other useful results from the previous video to remember that are going to be useful in this video. So e to the in theta plus e to the minus in theta is the same as 2 cos n theta. Or if you subtract them, e to the in theta minus e to the minus in theta, that's equal to 2i sine n theta. The proofs of those results, just a quick reminder if you're interested, are there. We did cover these in the previous video though. So again, I'll post a link to that in the description of this video if you need to go back and refresh yourself about those results. Now, those results are useful with what we're going to be doing today because they allow me to rewrite the sum of 2 complex numbers as a trigonometric function. So I can see that adding these 2 numbers together, these 2 complex numbers together, actually gives me a real number. This is real, there's no imaginary component there. In the next example, if I'm subtracting these 2 complex numbers together, I actually get a purely imaginary number. Or I could think of it as a real number multiplied by an imaginary number. So that could be quite useful later on. In the third example here, we can see that the way it's written at the moment is not particularly, it doesn't match up perfectly with these results. But there's a little trick I could do. I could factorise out e to the 3i theta. So the first term will become e to the 3i theta, because this times this is this. And the second term will become e to the minus 3i theta, because this times this is this. And by factorising out that e to the 3i theta, I can now use the results we've seen above to rewrite this as 2i sine 3 theta. So this might be a useful way of rewriting this. So here's the first example we're going to have a look at. We have been given the sum of these complex numbers. We've got e to the I theta plus e to the 2i theta plus e to the 3i theta, and so on, all the way up to e to the 8i theta. And part A of this question asks me to rewrite that sum in that form. So let me explain how to do that. First thing to note is this is a geometric series. because we've got first term e to the I theta, and then each time we're multiplying by e to the I theta. E to the I theta times e to the I theta is e to the 2I theta. E to the 2I theta multiplied by e to the I theta is e to the 3I theta, and so on and so on and so on. So we have a geometric series with first term e to the I theta, common ratio e to the I theta, and there are 8 terms in this sequence. First term, second term, third term, all the way up to the 8th term. So if I plug these values into the sum formula, so I have substituted the A in here, and the R in here, and the N in here, and that's given me this result. Then I've used that trick that I just mentioned to rewrite both the e to the 8I theta minus 1 and the e to the I theta minus 1. So first of all, let's just focus on the e to the 8I theta minus 1. I decided to factorise out the e to the 4I theta, which left on the inside e to the 4I theta minus e to the minus 4I theta, because this times this is this, and this times this is this. Note we've still got the e to the I theta at the front there. On the denominator, I decided to factorise out the e to the I theta over 2, because this times this is this, and this times this is this. Now, that's useful for me because now I can use our result. I can rewrite this as the 2I sine 4 theta. And I can rewrite this as 2I sine theta over 2. The other changes I've made here is I multiplied these two together to get e to the 5I theta. The final couple of steps here with this question is the 2 i's cancel out. I then did the e to the 5I theta divided by the e to the I theta over 2. So subtracting those powers, the 5I theta minus I theta over 2 is 4.5 theta, or 9I theta over 2. And this is the result we needed to prove. So that's part A done. Part B. We're then told to let P equal cos theta plus cos 2 theta plus cos 3 theta plus cos 8 theta. And we're told to let Q equal sine theta plus sine 2 theta plus sine 3 theta plus so on up to sine 8 theta. And we're then supposed to use our answer to part A to show that P, this P here, is actually this thing. And then we need to find similar expressions for Q and Q over P. So first, this P and this Q, Well, I'm going to start by writing P plus IQ. And the reason why I'm doing that, excuse me, is I noticed that if I multiply all of these terms by I to get IQ, I'd have I sine theta, I sine 2 theta, I sine 3 theta, and so on. And then by adding that to P, I would have cos theta plus I sine theta, cos 2 theta plus I sine 2 theta, cos 3 theta plus I sine 3 theta, and so on all the way up to cos 8 theta plus I sine 8 theta. I can then rewrite these in their exponential form so that I can use my result from the part A of the question. Because in part A of the question, I showed that this sum was equal to this. So P plus IQ is equal to this. What I've then done is I've rewritten the e to the 9I theta over 2 in its modulus argument form. So cos 9 theta over 2 plus I sine 9 theta over 2. And why have I done all of that? Well, comparing here, I can see that P is the real part of this sum. The real part of this sum is cos 9 theta over 2 times sine 4 theta over sine theta over 2. Which I could then rewrite as cos 9 theta times sine 4 theta times cosec theta over 2, because the sine is on the denominator there, and 1 over sine is cosec. And note, this is what we needed to show. Just as P is the real part of that sum, Q is the imaginary part of the sum. So Q is the sine 9 theta over 2 times sine 4 theta over sine theta over 2. Which again I can rewrite with the cosec. So that's my similar expression for Q. And the final part of the question, Q over P. Well, if I just take my answer for, I've actually written down P over Q there. That should be Q over P, the other way around. So these should be the other way around. It should be sine 9 theta over 2 over cos 9 theta over 2. And then we notice that we have the sine 4 thetas cancel out, the cosec theta over 2's cancel out, and we just get left with sine 9 theta over 2 over cos 9 theta over 2, which is tan 9 theta over 2. So, the useful thing for doing part A of this question, by rewriting the sum like this, it allows me to focus on the real parts and the imaginary parts separately, which then allows me to find what P and Q are. Second example for this video, we're told that Z, our complex number Z, is equal to cos pi over n plus I sine pi over n, where n is a positive integer. And we need to show that this sum, 1 plus z squared, and so on, up to z to the power n minus 1, is equal to 1 plus I cot pi over 2n. And here's how I'm going to do it. So first thing, I'm going to note that this is a geometric series. It has first term 1, it has common ratio z, and it has n terms, because this is the first term, second term, third term, all the way up to the nth term. So using the sum formula, I've got a times r to the power n minus 1 over r minus 1. Clearly that simplifies to be this. Then I think about what z is in this case. So I've rewritten this in its exponential form so that I can plug that into here and here. The e to the pi I over n to the power of n, so multiplying those powers together, I get e to the pi I. Now e to the pi I, we know that that's equal to minus 1. And minus 1 is minus 2. So carrying on over here now, the sum of this series is equal to minus 2 over e to the pi I over n minus 1. The next thing I did was I used that trick of factorising out the e to the pi I over 2n. This times this is this. The pi I over 2n plus pi I over 2n is pi I over n. And similarly, this times this is this. The next step, I noticed that this can be rewritten as 2i sine pi over 2n, using the result from the previous video. And the other thing I did at this stage is I moved this to the top with a negative power. Then the next line after this, I have rewritten this in modulus argument form. So I've got the cos pi over 2n minus I sine pi over 2n, minus because of the negative argument there. And then the last couple of steps, the 2's cancel out. I then decided to multiply top and bottom by I, excuse me, so that this I squared became minus 1. And then that's then going to cancel the minus there and there. Last step then, after that, we've got the I times cos pi over n divided by sine pi over 2m. That's the I cot pi over 2m. And then we've got the I times the minus I, which is minus I squared, which is positive 1. Positive 1 times the sine pi over n divided by sine pi over n is the 1. And this is the result we needed to show. So that's the second example we're doing in this video. One more example to do, which is this one here. Now notice this is a convergent infinite series. C and S being defined as such. So here is the first part of this question, where we are showing that C plus IS, so this series here, plus I times this series, and we need to show that's equal to 2 over 2 minus e to the I theta. So we start off with just the 1 at the front. Then we've got the half cos theta plus I times half sine theta. Then we have the quarter cos 2 theta plus a quarter I sine 2 theta. Then we have the 1/8 cos 3 theta plus I times 1/8 sine 3 theta. And so on and so on and so on. Then I note that I could rewrite this in its exponential form. Rewrite this in its exponential form. Rewrite this in its exponential form. And now I note, looking at all of this series here, that it's a geometric series. It's got first term A is 1, and the common ratio is a half e to the I theta, times this by half e to the I theta, times this by half e to the I theta, and so on and so on. Now, because this is an infinite geometric series and it does converge, I'm using the infinite sum formula, so A over 1 minus R. So A is 1 over 1 minus R. And then to simplify this, I'm just multiplying top and bottom of this by 2 to get rid of that fraction. So the 1 times 2, the 1 times 2, and the half e to the I theta times 2. So we have shown that C plus IS is equal to 2 over 2 minus e to the I theta. Now we're going to actually use a different trick for part B of the question, because the previous trick of factorising out doesn't work here. And I'm just going to show you quickly why. If I try to factorise out the e to the I theta over 2, I would have this expression here, because this times this is this times this is this. Then, just to make it super clear, I've also factorised out a minus, just so I've got the positive part here at the front. And notice the fact that there's this 2 here stops me from using this result. So I cannot do this factorising trick that we used with the previous 2 examples. There's a different trick I'm going to use. And that trick is like follows. I'm going to multiply the top and the bottom by 2 minus e to the minus I theta. So just copying the exact same thing down here, but with a minus power. What I will then get is on the top, the 2 times the 2 is the 4. The 2 times the minus e to the minus I theta is minus 2e to the minus I theta. And crucially, on the bottom, we've got the 2 times the 2, which is the 4. We've got the 2 times the minus e to the minus I theta, which is the minus 2e to the minus I theta. Then we've got the minus e to the I theta times 2. And then we've got the minus e to the I theta times minus e to the minus I theta. The two minuses make a positive, and those powers add to be 0. So we just get e to the power 0, which is just 1. What I can then do is the 4 plus the 1 is 5. And then if I factorise out this minus 2, on the inside I'm left with the e to the I theta plus e to the minus I theta. And now I can use our usual identity of replacing this with the 2 cos theta. So this is a slightly different little trick here of manipulating the denominator so that I am able to use this result. And notice once I've got to this stage down here, I've got the 5 minus 4 cos theta, which does start to look like what we wanted. Okay, carrying on from there, just to finish off this question then. So we've got my denominator matching up now. The numerator doesn't know, I need to do something about that. So I'm going to rewrite this e to the minus I theta in its modulus argument form. So rewriting it as cos theta minus I sine theta. Minus here because the argument is negative. Expanding those brackets out then, we've got the minus 2 times the cos theta. And we've got the minus 2 times the minus I sine theta, which is positive 2I sine theta. So I have shown that C plus IS is equal to all of this, which means that C has to be the real part of this. The real part of this is the 4 minus 2 cos theta over 5 minus 4 cos theta. The S is the imaginary part of this sum, which is the 2 sine theta over 5 minus 4 cos theta. And there we go, we've managed to show this, and we've found a similar expression for S. So that is how we can use the geometric series formulae for both the sum of a series and the sum of an infinite series with complex numbers in order to be able to rewrite those sums in different ways.